So hi everyone. Welcome to the very first video that I'm going to post. I apologize immediately for any sort of weird things that I say. I've put off trying to post these videos for quite some time because I absolutely hate the sound of my own voice, and trying to edit these things is something akin to being stuck in hell, but here we are. So this very first one is really about left recursion, which is a thing that I initially didn't really intend on covering in the class in any sort of explicit detail. But I assigned a homework problem, homework number 4, problem number 3, problem number 2, that does have left recursion in it. So that caused some confusion, and what I want to do right now is kind of explain what left recursion is, why it's important, how to get rid of it really quickly. I've also extended homework 4 to be due on Thursday instead of Tuesday, to give everybody a couple of extra days to sort of look at this video, look at the slides, make sure that they're kind of happy with what they're doing. So without further ado, we'll go through the slides really quick. So let's talk about left recursion. So on homework number 4, there is a grammar that has a particular production. It's the B production in that grammar that causes some significant amount of heartache. And the reason why this B production causes that heartache is because of what's called left recursion. There is fortunately a very common substitution that we can do to get rid of the left recursion and put it into both of the normal forms that you're supposed to be putting them into, or putting the grammar into for the homework problem. So first of all, I'm going to talk about what left recursion is kind of in a formal sense. So we call any production itself left recursive if it has a form like this. So if it is a non-terminal A going toward some non-terminal A followed by anything after that non-terminal. So if we go back, that's why this last B production, B derives capital B, capital A, lowercase a, is left recursive because it begins with the same variable that's deriving that sentential form. So if we have a left recursive production, then we can also call a sentential form left recursive if there is some left recursive production in the middle of it. So for example, if you start with some start symbol and you can go to a sentential form that has that start symbol to the very left part of the right hand side, that sentential form itself is called a left recursive derivation. And so finally, if you have a grammar and that grammar has a left recursive production inside of it, just one of them, that means that the grammar itself is left recursive. So left recursion is not a great situation, and the reason is that top-down parsing, which is one of the very most common ways of generating a parse tree to begin with, can't actually handle a left recursion. Left recursion causes these parsing algorithms to effectively either get stuck or not be able to derive from the very beginning, or just kind of break. So what has to happen is, prior to using a top-down parsing technique, you actually have to get rid of the left recursion using some substitution that results in an equivalent grammar. So we've seen this kind of thing before when we talked about all of the different substitutions that you can use to get rid of things like lambda productions, like unit productions, and those sort of very specific forms that we were trying to get rid of before to make parsing easier. This is just another sort of additional substitution that we can do to get rid of this specific kind of bad production. So in general, in the wide world of recursion, there are two different types of left recursion. There's what's called direct left recursion, which is exactly what we've been talking about, right? So you have a variable, and on the right-hand side of some production, beginning with that variable, you have the variable itself. That is direct left recursion. There's also indirect left recursion, which happens where you can go through some unit productions and get from a variable to an effectively equivalent variable at the left-hand side of the right-hand side of a production. Indirect recursion happens through these sort of multiple substitutions, typically with the unit production, and we're not going to necessarily discuss them here. It's just good to know that they actually exist. So this is kind of what I alluded to kind of early in the class. These kind of things tend to be extremely deep when you wade into them. And so while this substitution mechanism or this method gets rid of a direct left recursion, there are some additional things that you have to do in order to take care of indirect recursion, which you might see in the graduate level class. So the general gist or the idea of how to get rid of left recursion is to try to replace that recursive production that might look something like this with two new sets of productions, one of which just happens to be right recursive. So we've talked about left recursion. Right recursion is exactly what you would think it would be. Instead of being on the left-hand side of the right-hand side, the variable is now on the right-hand side of the right-hand side, as you can see in this second production here. So this, when you look at it, it seems kind of mysterious. It is kind of magical. And so what we want to kind of do is go through the intuition behind how somebody just kind of came up with this substitution out of nowhere. So the idea is, if you look at this left recursion as a kind of loop that you're going through in a program, for example, you can rewrite that loop to begin at 1 or begin at 15 or 50 or 75 or whatever by effectively rewriting what the beginning of that loop looks like. And so what we're going to do is we're going to basically make the parable that if we're trying to prefix a whole bunch of strings with a variable string, we can, instead of starting at 0, we can start with a hard-coded initial value and then postfix that string with one fewer iterations through the loop. And so that might make sense just in words, but it probably makes more sense to actually see it in code. So we can think about these recursive productions as something like this, right? So we have some loop, and what we're trying to do is we're trying to append some characters to that string using just a standard sort of for loop. So I think all of us would agree that it is equivalent to begin with a single plus sign as the initial value for the string variable str, and then loop through the for loop one fewer times and append a sort of suffixed plus sign. And so this suffixing step at the very end, or this part right here, is exactly what that second production in the substitution is actually doing. What we're doing is we're saying we can replace left recursion with right recursion as long as we set the initial variable up to have some initial value that is all of these sentential forms or all of the right-hand sides of productions that are not left recursive. So to generalize that substitution, effectively that beta that we saw way back here, this beta here, it represents all of the right-hand sides of these productions that are not left recursive. So you would effectively have to do this same substitution for any production that is left recursive, even if there are multiple A productions that are left recursive. So what we're going to do as a sort of cap off to this video and sort of the very small conversation about left recursion is talk about an extremely famous example of getting rid of left recursion and why getting rid of left recursion is important. So we've already talked about how context-free languages allow us to implement a large portion of programming languages. And in particular, arithmetic expressions are a really great example of not only ambiguity, but also where left recursion very commonly occurs. So here you can see the sort of standard arithmetic expression grammar for every programming language you can probably think of. If you kind of take the naive route to generate that grammar, you're going to end up with two different left recursive productions. You're going to have this capital E yielding an E plus a T, and you're going to have this capital T yielding a T times an F. So what we're going to have to do is we're going to have to take this grammar and apply that same substitution that we talked about just a couple slides ago twice in order to get rid of both of these left recursive productions and replace them with their right recursive counterparts. So the fact of the matter is that this grammar appears all over the place. And despite its popularity, it's also left recursive, which means that you will very commonly see the version of the grammar that we're about to derive ourselves. So for these E recursions, what we can do is we can recognize from our sort of formula that we have in the previous slides, the A variable in that substitution formula is our E. The alpha is going to be our plus T, and our beta, or our non-recursive right-hand sides, well, that's just the variable T. So if we plug those values into the formula, we're going to get that our E production is going to be replaced with that beta, or that T, and our new right recursive variable E prime. Then we're going to have our alpha, which is plus T, appended to our new right recursive variable E prime, and then we're also always going to have this lambda. So what we see here is that by doing the substitution in order to get rid of the left recursion, we're always kind of introducing this lambda production that ultimately has to be removed if the task is to turn this grammar into Chomsky normal form or Greenblatt normal form. So we can do exactly the same thing with our T variable. So here we have exactly the same thing, right? So our A variable is going to now be T. This is the left recursive variable. Our multiply sign or times F is going to be alpha, which is the suffix of the left recursive production right-hand side. And then the beta is going to be F, which is the non-left recursive right-hand side production. So plugging that in, we're going to get T on the left-hand side. On the right-hand side, we're going to get F, which is our beta, then appended to our T prime, which is our new right recursive variable. Then we're going to get the beta suffixed with that new right recursive variable, and then again just a lambda as well. So if we put all of those things together, this is an equivalent grammar that is no longer left recursive. So the important things to note are that indeed this thing is not left recursive. So E does not have an E on the left-hand side of any of the right-hand sides. There are no E primes on the left-hand side of the right-hand side. There are no T's, no T primes, or no F's on the left-hand or the left-hand side of the right-hand sides. So we've kind of ensured that we've actually done the job of getting rid of the left-hand or the left recursion. The thing to keep in mind, though, is like I was saying before, we are introducing these lambda productions. So typically what needs to happen is you need to identify left recursion and attempt to get rid of it at the very beginning of the problem. The reason is because you don't necessarily want to have to go through and remove lambda productions multiple times, and you don't necessarily want to have to deal with getting rid of left recursion after you've added a whole bunch of productions in order to get rid of unit productions and things like that. So typically it makes your life way easier if you get rid of left recursion at the very beginning, and then you go through all of the sort of steps that we've gone through for the rest of the class. So doing things like removing lambda productions, removing unit productions, and then rearranging productions to get to either Griebach normal or Chomsky normal form, whichever one you're trying to aim for. So that kind of wraps this up. Hopefully this is a fairly short video that kind of gives you an idea of how things are going to go forward. Hopefully they're going to get smoother as I get used to doing this kind of thing, talking to myself in an empty room to a computer. And so I hope that it's helpful, and if it's not, please send me an email and tell me it's not helpful. Please send me any suggestions that you have to make it better. I'd really appreciate it. So thank you for watching, and I will see you soon.